My name is Michael Katz, and I will talk today about our joint work with Gabriele Röger and Malte Helmert on shortest cost optimal planning. For the purpose of this work, it is sufficient to talk about labeled transition systems. Planning task over an LTS is a tuple of states, actions, deterministic transitions with no negative costs, initial state, and a set of goal states. For a transition SAT, we say that A is applicable in S and T is the state that results from applying A in S. A plan is a sequence of actions consecutively applicable in the initial state and resulting in a goal state. The purpose of cost optimal planning is to find a plan with minimal possible cost. This work is about shortest cost optimal planning, and here we are interested in finding a shortest in the number of actions among the cost optimal plans. Research in classical planning usually deals with either cost optimal or satisficing or agile planning, and there are many planners developed for these settings. There is even some work on multi-objective planning. These, however, do not meet some of the existing needs, as previous work has established a need for a shortest cost optimal planner. The soundness of the algorithm presented in that work depends on the use of a shortest cost optimal planner at each iteration. Luckily, there is an existing work on a cost algebraic heuristic search, which in principle is applicable to our setting. But to the best of our knowledge, no implementation of cost algebraic heuristic search of shortest cost optimal planning currently exists. Our contributions are therefore as follows. We formulate the shortest cost optimal planning problem and implement the cost algebraic A* for shortest cost optimal planning. Additionally, we propose an alternative approach based on cost transformation. In some settings, these two different approaches have the same expansion order, which we formally show. Finally, we perform an extensive empirical evaluation of the suggested approaches. Let's start with the cost algebraic approach. We define a heuristic for cost algebraic planning problems to be a mapping from states to pairs of non-negative values, hc for costs and hd for distances. Such a heuristic is admissible if it does not over-approximate the cost and the distance of a shortest cost optimal plan. To compute an admissible heuristic, we can use any admissible heuristic for pi for cost estimate and any admissible heuristic for a transformed to unit cost task for a distance estimate. Note that such an approximation can be lower than necessary, since it estimates the shortest distance of any plan, not just of cost optimal ones. As it is not clear whether the extra effort of keeping an additional transformation and computing another heuristic pays off, we can also simply use the blind estimate. Cost algebraic A* is different from the regular A* in two aspects. First, the open list is ordered by pairs FC-FD, where FC is the sum of GC, the cost of the path to the node, and HC, the cost heuristic. FD is the sum of GD, the distance to the node, and HD, the distance heuristic. FC-FD is preferred over FC'-FD' if FC is smaller than FC', or they are equal, but the distance FD is smaller than FD'. The second difference is in the reopening condition. In addition to the regular condition of GC smaller than GC', if they are equal and GD is smaller than GD', we also reopen. As we mentioned above, it is not clear whether having a non-blind estimate pays off. Here, we test this empirically for a large collection of admissible heuristics. CA0 stands for the configuration with a blind estimate, while CA stands for a configuration using the same heuristic on distance transform tasks. While there is no clear dominance on all domains, overall having the additional non-blind distance heuristics does not seem to pay off. Looking deeper on LMCAT results, while there is a significant improvement in terms of expanded nodes, it does not compensate for the much longer per node computation time. Moving on to the cost transformation approach, it is possible to transform the costs of any given planning task so that the cost optimal plans of the transformed task are shortest cost optimal plans for the original task. The idea is to increase the cost of each action by a small constant epsilon. That way, the cost of a plan with n actions increases by n times epsilon. The idea is not new and has been used in other contexts. We can always choose epsilon sufficiently small to ensure that the order among the action sequences is preserved. If you want to have integer costs, as some planners support only integer costs, with a large enough m, that can be done. Note that the resulting transformed costs can be quite large. Solving the cost transform task with heuristic search, we have a few options for heuristic computation. We could compute the heuristic on the transformed task, but then some heuristics may be sensitive to large costs. Or we could compute the heuristic on the original task and scale the heuristic value multiplying by m. The following theorem states that the scaled estimate is admissible in the transformed task. Comparing empirically the two variants of heuristic computation, CT stands for heuristic on cost transformed task, and WCT denotes the scaled heuristic on original task. These two approaches are quite complementary, with WCT working slightly better overall. Looking again at LMCAT, this is due to significantly increased heuristic computation time. And while the number of expansions is smaller for CT, it is not reflected in the coverage. It is worth noting that the cost algebraic approach that uses a blind heuristic expands nodes in exactly the same order as the cost transformation approach that computes the heuristic on the original task, scaled. But that doesn't mean that the two approaches perform the same in practice. The overall coverage is quite similar for the two approaches across tested heuristics. But the memory consumption is clearly larger for the cost algebraic approach. Therefore, the cost transformation approach performs slightly better. To sum up, we define a new and interesting computational problem of shortest cost optimal planning and implement a planner based on previously suggested cost algebraic A-star. Additionally, we propose an alternative approach based on cost transformation and empirically compare the two approaches in various settings, exploring their strong sides and weaknesses. There are many interesting open questions for future work remain. Some of these are how to efficiently compute both cost-based and distance-based heuristics for the cost algebraic setting. What's the right scaling value m? And adaptation of search pruning techniques to the cost algebraic setting. Thank you.